morning, this is B. Naresh, working as assistant professor in the EC department. And today's topic is positive peak and negative peak clampers here. So before going to this clampers here, actually what is the purpose of the clamper and what is the clamper? So for this clamper circuit, we are going to use the two components like that is capacitor and diode. So means we are going to design this clamper circuit by using the PN junction diode along with a passive component that is capacitor. And in this network, here the input signal is passing through the capacitive element. And we know that based on the functioning of the capacitor allows only the AC signal and blocks the DC signal here. So that is the reason when an input signal is passing through the capacitive element, it loses the DC component here. So hence, at the latter, we need to reinsert the DC component or we need to restore the DC component in a output waveform that can be done through the clamping circuit here. So that is the reason. So here I define the statement of the clamper here. When a signal is transmitted through a capacitive coupling network, it loses its DC component and a clamping circuit may be used to introduce a DC component by fixing the positive or negative extremity of that waveform to some reference level. So based on this, this clamping circuit, so based on the statement of the clamping, so the clamping is either to restore the DC component either at the positive portion of the given waveform or a negative portion of the waveform here. So that is the reason. It is also called as a DC restorer or DC reinserter circuit. So then, and coming to your, so based on this, these clampers are classified into two types. One is represented as a negative clamping. Another one is represented as a positive clamping. This negative clamping is also called as positive peak clamper. And positive clamping is also called as negative peak clamper circuit. So majorly we are under these two types of the clamping circuits. One is positive peak clamper or it is also called as negative clamping. Another one is negative peak clamper, it is also called as positive clamping. So we'll see one by one in detail why it is called as a negative clamping or a positive clamping, or it is also called as positive peak clamper or a negative peak clamper with respect to the negative clamping as well as the positive clamping here. And one more point, in this clamping circuit, it doesn't shape the waveform here. It looks like your given input signal, but the only the thing is to you, it changes the DC level here. But in an input signal, the DC level is represented as, or the average value of the given input signal is represented as your 0. But in output signal, that average value, either it will be shifted in a positive portion or your negative portion, but it doesn't changes the shape of your waveform here. Now coming to your, the first, the positive peak clamper or a negative clamping here. So this clamper circuit consists of, majorly it consists of diode and a resistor as well as the capacitor here. So by using these three components, we are going to build a clamping circuit, and this clamping circuit can be used to shift the DC level at the negative portion of the given input signal. So that is the reason this type of the clamping circuit is called as a positive peak clamper or a negative clamping here. Now we'll see the circuit of negative clamping or a positive peak clamper here. So let us consider this is the circuit for a negative clamping. It is also called as a positive peak clamper. And this network consists the three components. So here one is the capacitor, one is the diode, and one is the resistor. Now the input signal is passing through the capacitive element, and output is measured across this load resistance. Here I represented as your RA. And here we are going to apply input signal is a sinusoidal signal, hence this is represented as VI is represented as Vm sin omega t. And here for this input signal, we consider the duration is 0 to 2 pi. So here the half duration is 0 to pi. Another half duration is pi to 2 pi. And here the signal is represented as your input signal. It is linearly changes with respect to your time period here. So here I'm coming to the circuit operation. And whenever the input signal is passing through this capacitive element, it allows the only the AC signal and it blocks the DC portion. So here, if you observe this graphical representation of your input signal, so here this is represented as this zero line is represented as a DC line, or it is also called as the average value. Average value or a DC component is zero for a given input signal. For a given input signal, the average value or a DC component is zero. Whenever this type of the signal is passing through this capacitor, it blocks the DC component and it allows only the AC component that is passing through this diode here. Then at the later at output state, this circuit is also restores the DC component either in a positive portion or a negative portion. But here, based on the circuit construction, the DC level is adjusted at the negative portion. Hence, this type of the clamping is called as your negative clamping circuit. Now, coming to you, we'll see what happens in this negative clamping. Then, why it is called as negative clamping or a positive peak clamper circuit. So, for this case, let us say this is called positive peak clamper. And let us consider the durations here with respect to your input signal. And here we represented as this is the Vi, 0, this is pi, and the 2 pi. Let us consider the quarter cycles also here. And here, so, and let us take this is 0 to pi by 2, pi by 2 pi, and this is 3 pi by 2, and 2 pi duration here. And based on the utilization of the diode in a circuit, and here it is represented as anode, and here it is represented as your cathode. And we know that, so when the diode is conducting, if the anode voltage of a PN diode is greater than or equal to cathode voltage, then we can say that diode is in a conducting state here. Otherwise, diode is in a non-conducting state. So hence, for this diode, for a given diode, we should verify this. The anode voltage must be greater than or equal to cathode voltage. Then only we can say that diode is acts as a conducting state here. So means that in that state, the diode is replaced with the on state. Or this on state is replaced with a short circuit model, either in an ideal case or a practical case. So if it is ideal case, simply we consider that short circuit. If it is a practical, it offers the diode forward resistance along with the cutting voltage of diode. Now we'll see what happens during the positive off cycle and during the negative off cycle, and what is the functioning of diode here. And based on this utilization of the diode in this circuit, whenever the input signal having the positive portion, means this 0 to pi duration, 0 to pi duration. So this means the anode contains a peak voltage, a positive peak voltage is represented as a Vm. So during this 0 to pi duration, anode voltage becomes larger with respect to cathode voltage. Hence, diode enters into the forward bias mode. Hence, diode acts as a conducting state. So under this conducting state, diode is replaced with a short circuit model. Similarly, during this pi to 2 pi duration, during this pi to 2 pi duration, the input signal is linearly changes towards a negative voltage and again towards a zero voltage, minus Vm, 0 to minus Vm. Again, this is Vm, but magnitude is polarity is a negative. So then this this pi to 2 pi duration, the input signal is changing from 0 to minus Vm, again minus Vm to 0. During this cycle, diode gets reverse biased operation. So why? Because of that, the anode voltage is less than of your cathode voltage. Hence, under this duration, the diode acts as a reverse biased diode. Hence, the state is represented as your non-conducting state. So that is the reason. During this pi to 2 pi duration, diode acts as a non-conducting state here. So if it is a non-conducting state, it is replaced with, means the state is represented as offstream, means there is no conduction across the diode. That is the reason this state is replaced with the open circuit model. Similarly, what we observe here, 0 to pi duration, diode acts as a conducting mode. Why? Because of the diode enters into the forward bias mode configuration here. So hence, at this point, diode acts as a conducting mode. The state is represented as your on state. If it is on state, here it is replaced with the short circuit mode. But we'll see what happens in the capacitor during this positive portion and during the negative portion here. So for this case, we need to observe the functionality across this capacitive element here. So based on this, we need to analyze the each quarter interval. So with respect to each quarter interval, what happens in a capacitor with respect to your diode function. So let us consider. So here I consider the interval is 0 to pi by 2 interval. So here I consider a 0 to pi by 2 interval. In this, let us assume that initially this capacitor is fully discharged. Initially the capacitor is fully discharged. And based on this assumption, and we consider the interval is 0 to pi by 2 interval. At this interval, the input signal is changing from 0 to Vm voltage. So here the input signal is changing from 0 to Vm voltage. So what happens here in the capacitor? So initially capacitor is fully discharged. Hence now the capacitor, the function is charging towards the maximum voltage. So at this point, so whenever the input signal is changing from 0 to Vm voltage, the capacitor is also charging towards the maximum voltage. So here from this representation, the maximum voltage is represented as your Vm. Hence, so here the capacitor is charged towards the Vm voltage. So at this point, diode is again conducting here. So across this point, we need to observe the output voltage. So that is the reason. This 0 to pi by 2 interval, capacitor is charged towards Vm here. So this is the maximum voltage. Now we'll see what happens during the interval is pi by 2 to pi interval. So during this interval, pi by 2 to pi interval, now let's first see what happens in the input portion. The input portion is, so here the input portion is linearly changing from Vm voltage to your 0 volt. Means your input signal is linearly decreasing towards your 0 voltage. But up to this Vm voltage, the capacitor is holds the maximum voltage. So hence, so up to the peak voltage, when the VA is reached to Vm voltage, what is the capacitor function? Under this condition, capacitor is charged towards the Vm, hence capacitor contains a maximum voltage. So at this point, when VA is reached to Vm, the voltage across the capacitor is represented as your maximum voltage. Hence, I represented as the voltage across the capacitor is represented as your Vm. But initially that is a fully discharged. But whenever the VA is reached to Vm, the capacitor is also charged towards the maximum voltage. Hence, from that concept, the voltage across the capacitor, VC means the voltage across the capacitor is represented as your maximum peak voltage. That maximum peak voltage here it is represented as your Vm. Now we'll see this pi by 2 pi interval. Your input is linearly decreasing towards a 0 voltage, but let us take. So now what happens here? The capacitor, if the capacitor is fully charged, it acts as a voltage source, or it looks like your battery. So if the battery is fully charged, then what happens here? Now the battery condition is discharging towards your minimum voltage. So similarly, when a capacitor is fully charged, the nature of this capacitor is now trying to discharge towards the minimum voltage. But here we need to maintain the discharging time period should be very very large. We need to maintain the discharging time period is very very large. So how we are going to define the discharging time period? So that can be defined with respect to your used components here. For a circuit, the components are, we use this passive components is, one is the resistor, one is the capacitor. So based on this, it looks like one RC circuit ends from the representation. The time constant, here it is represented as a tau. The tau is represented as the product of resistance and the capacitance. The time constant is represented as the product of resistance and your capacitance. So then here, a condition should be this discharging time period should be much greater than of your given input signal time period, where t is small t is your input signal time period, tau is time constant of a given circuit. So here we made as the tau is much greater than of your input signal t, means we are making the discharging time period should be very large with respect to your given input signal. So what happens if the discharging time period is we maintain is a very large, means that it requires more time to attain a minimum value. So based on this time constant, it indicates that the capacitor discharging time is requires more time period to attain a minimum value. So that is the reason. Based on this analysis, based on this assumption, so here the input signal is fastly decreasing or discharging towards your zero, but we maintain that the capacitor discharge time period is a very very long. So hence slowly discharging towards your minimum voltage. But even though it very fastly your input signal is reached to zero, but a capacitor is slowly discharging towards zero. Under this point, we assumed as the capacitor holds the same value. So under this condition, capacitor is slowly discharging towards 0 ends, and at this point now we consider the voltage across the capacitor is approximately equal to your V. So based on that, here I'm going to redraw the equivalent circuit. So for this case, I'm going to consider the equivalent circuit. So now this capacitor is replaced with a voltage source, and this contains a voltage is represented the Vm, and diode is conducting and is replaced with a short circuit, and again then it contains a parallel resistance is R, and here we are applying the Vi, and now we are going to measure a V. So this is the equivalent circuit under when the diode is conducting mode here. So now we need to write the mathematical relation, and from that mathematical relation we need to observe the output voltage of this positive peak clamper or a negative clamping circuit, which can apply the KVL. So what happens here? VA is equal to, now we need to find out. So this is capacitor. So means the voltage across the capacitor plus voltage across this resistor. So which current is the flows here? Diode is a forward bias, hence it offers the current I represented as I. Now from this, I am rewriting this equation. VA is equal to the voltage at the capacitor, and VR means I into your RA. Now again, from the circuit, now I am going to find out this output voltage. So what is output voltage? V0 is equal to your, this V0 is parallelly with respect to this resistance. So here we need to find out the voltage drop across this resistance is represented as I into your R. Hence, from the circuit, we observe this. The output voltage is a product of current and resistance here. Now I'm going to substitute this in this relation. So what happens here? So now I consider this relation. VI is represented as VC plus IR. So now this IR is replaced with this V0 equation. So hence VI is equal to VC plus V0. Now from this relation, I am going to observe the output voltage V0 is equal to Vi minus Vc. And we know that at this point, when the diode is conducting, the voltage across the capacitor is represented as your maximum voltage. That maximum voltage is reached up to your Vm. So hence, so Vc is replaced with your peak voltage. So that is represented as your Vm. So this is the final output expression. So for this clamping circuit, now we need to observe what happens with respect to your given input signal. So now we'll need to check. So with respect to your, so now we got this one, this relation, the mathematical relation. V0 is represented as Vi minus your Vm. Now we'll check if you consider this input signal, and let's take this is the input signal. So we consider the quarter duration 0. This is pi by 2 and pi, and this is 3 pi by 2, and this duration is 2 pi. So for each quarter cycle, we need to identify the magnitude of given input signal. With respect to that given magnitude, we need to observe the output voltage. Let us take, if our input is a 0, now we can substitute here. The mathematical relation is V0 is Vi minus your m. It's the potential difference between input voltage and the peak voltage. So your Vi is a 0, 0 minus Vm, that V0 is equal to, it becomes minus Vm. So this one. And similarly, we need to observe when the input voltage is reached to the peak voltage in a positive direction. So hence, here I consider if the input voltage is equal to Vm, now what is the output relation? V0 is represented as Vi minus Vm. So here I consider Vi is the Vm, hence Vi is replaced with the Vm, again minus Vm. So Vm is a get cancel, the output voltage is 0 here. At this point, the output voltage is represented as 0. Similarly, at 3 pi by 2 condition, your input is reached to your minus Vm. Now we need to observe the output voltage across this point. So hence V0 is equal to VA minus VM. Your VA is reached to minus VM, hence again minus of minus VM, then becomes minus 2VM. So these are the three parameters we observe with respect to your given input signal. Now, by using this output representation, we need to draw the response of this positive peak clamp or a negative clamping. Then we need to identify why it is called as positive peak clamp or a negative clamping. So for this case, let us consider with respect to your input signal, we need to draw the response here. So here I consider, and let us take this is VM. Again, this is another VM, means the portion is a negative portion. And let's take this is input signal. And please take in all the intervals here. So this is 0, this is pi by 2, and this is pi duration. And this duration is 3 pi by 2. And this is again 2 pi. So now this is periodic signal is repeated here. Again, this is now we'll see what happens with respect to all these magnitudes. We observe the VA is a 0, V0 we observe is a minus VM. When VA is a VM, we observe that V0 is equal to 0. When VA is a minus VM, we observe that V0 is equal to minus 2 VM. Now we see first, at this point, when VA is a VM, so what is output voltage you observe? Your V0 is represented as your 0, means at this point, the output voltage is 0. Now similarly, now at this point, VA is a 0, the VA is 0, V0 is represented as minus VM, means when input signal changing from plus VM to 0, output is changes from 0 to your minus VM. So hence, we need to draw the response. The output voltage is changing from 0 to minus VM. So hence, at this point, the output is previous state is output is 0. At this point, the output is reached to minus VM. So hence, this is 0 means minus VM is in the bottom portion. So here I'm going to draw towards minus VM. Let us take this is 0 and this is minus VM. So similarly, when VA is a minus VM at this point, at this node, if the VA is minus VM, what is output voltage here? Minus 2 VM means, so previously when VA is a 0, output is at minus VM. When VA is a minus VM, now output changes to minus 2 VM, means the output signal changing from minus VM to minus 2 VM, means again further minus VM is increases here. So hence it is again further it is changes. So another this is minus VM here. So the total net voltage is your 2 VM minus 2 VM here. Now again when VA is changing from minus VM to 0 here. So what happens here when the VM is changing from minus VM to 0 means VM is a 0. Output is again minus VM. So hence from this minus 2 VM to again it changes to your minus VM. Now again when VA is a VM, output is 0. Again this is equals to your 0. So like that, it periodically it changes like this. Now you can observe this is the 0 line and this is minus VM line and this is your minus 2 VM line. Now we need to identify how we can say this is the negative clamping or a positive peak clamp. If you observe this input waveform and output waveform, this is output waveform. Both are looks like there is no change in a shape, but the thing is to your what is the clamper circuit? So the clamper circuit is used to restore the DC output or a DC signal at the output waveform. Now we need to identify that where is the DC signal. So further case, we need to identify with respect to your input signal. if you observe the given input signal, the average value or a DC component of a given input signal is represented as your zero. Hence, at which VA is a zero, what is the output voltage we need to find out. So we already observed that when the VA is a zero, the output voltage of the clamper signal is represented as your minus VA. Hence, so here the DC level at VA is a zero level, the output is represented as a minus VA. Hence, the DC level now is adjusted at this is the DC level. So with respect to your given input signal. So with respect to your given input signal, the DC level now is adjusted at the minus Vm. So hence, so where is the DC level here? The DC level is adjusted at the negative portion. So that is the reason this type of the clamping circuit is called as negative clamping. Then why it is called as a positive peak clamper means entire the positive portion is shift towards your negative side. That is the reason. You can observe this one. This entire wave is this Vm magnitude is shift towards the bottom, entire in the negative peak. So that is the reason it is also called as positive peak clamper or negative clamping here. Now we'll see the another clamping circuit is a negative peak clamper or a positive clamping. So just now we discussed that what is the negative clamping and why it is called as a negative clamping or how it is acts as a positive peak clamper. Now we'll see the another clamping concept is negative peak clamper or a positive clamping. So in this positive clamping, the entire the portion of the negative peak signal should be shift towards the positive direction or rise above the zero level, and that type of the clamping is called as your positively clamped or a negative peak clamping. Then how we can satisfy this positive clamping? So whatever the clamping circuit, it uses the same components. So like that is capacitor and diode and resistor. How we can change the functionality of this circuit? So for this case, the only thing is that we need to change the diode utilization. If you observe this the negative clamping circuit, so diode is modeled in a forward biasing model. Means anode is connected to the cathode, means capacitor negative terminal. Cathode is to be grounded. So in this case, I'm going to revert the diode. Then we need to analyze the functioning of the clamping circuit. So the only the difference is if you observe a negative clamping and a positive clamping, here the diode is reversed here. So in a previous circuit, the anode of the diode is connected to capacitor on the other end, but here the cathode of the diode is connected to this capacitor on the other end here. So now this node is cathode and here it is anode. Here anode is grounded, but in the previous circuit, cathode is the ground. Now the definition is the same. Again, your input signal is passing through this capacitive element. It blocks the DC component. Then at the latter, it restores the DC component or it reinsert the DC component in the output waveform. But here, due to this positive clamping, the DC level is adjusted in a positive portion of a given output waveform. That the reason it is called as your positive clamping, or it is also called as your negative peak clamper circuit. Now we'll see what happens. And based on the utilization of this diode here, so we know that when the diode is conducting and diode is non-conducting, the basic rule is if the anode voltage is must be greater than or equal to cathode voltage, then only we can say the diode is conducting state here. Otherwise, diode is your non-conducting state here. So here there are the two peaks here. So 0 to pi duration and pi to 2 pi duration in an input signal. If you consider this 0 to pi duration, the input is towards the positive peak voltage And this pi to 2 pi duration, the input is changing towards the minus Vm or negative input negative portion here. And here anode is connected to ground means anode voltage is 0, means the cathode voltage should be less than of this 0 voltage, then only diode is acts as your conducting state here. So for this case, and based on this working principle of the diode, first we need to identify at which portion diode becomes the conducting state here, either a 0 to pi duration or a pi to 2 pi duration here. So for this case, let us consider if the duration is a 0 to pi duration. So what happens here, more positive voltage is passing through your cathode of the diode compared with your anode signal. Why? Because of this is here it is represented as your Vm voltage here, positive Vm voltage or peak voltage. So whenever the input signal is under the positive direction, so that positive peak is passing through the cathode of the diode. So but anode should be connected to your ground here, that is 0. So hence, so what happens here during the positive off cycle, more voltage across your more positive voltage across the cathode compared with your anode. Hence, during the positive off cycle, diode is enters into your non-conducting state here. So if the diode is a non-conducting state, so here it is replaced with your open circuit. It means capacitor is not charging or discharging towards the maximum or minimum with respect to the charging and your discharge. So when this diode is a conducting, means whenever when input signal is changing from 0 to minus Vm or minus Vm to 0, means the within the interval of pi to 2 pi interval. So what happens here, the more negative voltage is passing through cathode with respect to your anode here. So your anode is connected to 0, hence, and the cathode is now contains a negative portion. That is the reason. So what happens here, anode voltage becomes larger compared with your cathode voltage. Hence, from this point, now the diode is enters into your conducting state here. So under this condition, now we need to analyze the response of the given clamping circuit. Now we'll see what happens. So let us consider again a pi to 3 pi to duration, pi to 3 pi by 2 duration. But in an entire pi to 2 pi duration, the diode is a conducting state. But we need to check what happens in the capacitor function. So that is the reason I consider the quarter intervals here. So pi to 3 pi to duration here. So in this duration, now the diode is acts as a conducting state, but now we need to identify that what is the capacitor function. So initially capacitor is fully discharged. Initially capacitor is fully discharged. So when the diode is a conducting, so what happens here, now anode is connected to this node. So hence now the current is flow is like this, and this current here it is represented as your forward current. So now what happens here, this is plus, now it becomes your minus here. So now the capacitor function is at this point, now the capacitor is charging towards Vm. Which Vm here? The magnitude is minus Vm. So why? Because input signal is also changing from 0 to minus Vm. That is the reason. The capacitor is also charging towards your maximum voltage here. So that maximum voltage is represented as your minus Vm here. Then we'll see what happens during the interval of 3 pi by 2 pi interval. So what happens here, up to this 3 pi by 2 interval, capacitor is fully charged. So that fully charged voltage here we represented as your Vm. Now if the capacitor is fully charged, it acts as a voltage source. Now the function is, the nature of that one is to discharge towards your minimum value. So for this case, again, we need to make the discharge time period should be very large compared with your given input signal. Hence, here I consider that the tau is much greater than of t. So under this point, so what happens here? But input signal is changing from minus Vm to 0 fastly. But capacitor is slowly discharging towards the minimum 0 voltage here. Or capacitor is slowly attaining to your 0 voltage. So from that point, we consider that the voltage across the capacitor is represented as your Vm. So by using this principle, here I'm going to redraw the circuit. So then, so here I'm going to rewrite this equation. So I'm going to redraw the circuit. So here this is minus and plus. This is the capacitor. But we know that the voltage across the capacitor is Vm and diode is short circuited. Then the parallel resistance is R, and here it is represented as Vi. And here now we are going to observe the V. Now the current is flows like this during the forward cycle. Now from this circuit, what we need to write, just apply the KVL here. So what happens here, VI is equal to, from this circuit, VI is equal to the voltage across the capacitor along with the voltage across this resistance, hence VC plus VI. Now if you want to write in terms of current, VI is equal to voltage across the capacitor plus, it should be represented as your I into R. Now from the circuit, again, from the circuit, now I'm going to find out the output voltage, that is a V0. So what is V0? This V0 is proportional to this resistance. So means we need to find out the voltage drop across this resistance. Voltage drop across this resistance here. So how to write this one? The voltage drop across the resistance, that should be represented as your I into R. Now I'm going to substitute this I into R in this equation. So what happens here? VA is equal to VC plus this IR is replaced with the V0. Now from this relation, now I'm going to observe the output voltage V0 is equal to, so V0 is equal to Vi minus your Vc. But at this 3 pi by 2 interval, whenever the Vi is reached to minus Vm, the capacitor is also charged to the maximum voltage, that is a Vm, but here the input direction is minus Vm. Hence, the capacitor is also charged towards the minus Vm voltage. Hence, the voltage across the capacitor is represented as your minus Vm. Hence, Vi minus of this voltage across the capacitor. This polarity, you can observe this polarity here. So the current flowing like this. So hence, this is minus and plus. Hence, the voltage across this capacitor is represented as your minus Vm. Hence, it is minus Vm. Now, what happens here? V0 becomes to your Vi plus Vm here. So, this is the final the output expression based on this positive clamping circuit here. Now, we'll see what happens with respect to your magnitudes here. So, now we'll just now we observe this mathematical relation. V0 is represented as Vi plus Vm. Now, we'll check it. So, what happens if the Vi is a 0? So, if Vi is a 0, now what happens? V0 relation is Vi plus Vm, means 0 plus Vm, that becomes to your Vm here. So then similarly, if Vi is equal to Vm, then we need to find out the output voltage. What is the V0? So V0 is equal to Vi plus Vm, means Vi is a Vm, again Vm, means it becomes your 2Vm. Similarly, if Vi is a minus Vm, so what happens? V0 is equal to Vi is a minus Vm plus Vm. So Vm and this minus Vm will get cancelled. The answer is 0. So these are the three parameters we observed with respect to your mathematical relation of output expression. So Vi is a 0, V0 is represented as a Vm. Vi is a Vm, V0 is represented as a 2Vm. If the Vi is minus Vm, V0 is represented as 0. By using these, now we are going to draw the circuit graph clamping circuit response here. So let's consider for this case again. So So let's say this is my VA signal, input signal, and this is 0, and this duration is represented as pi by 2, and here this duration is represented as the pi, and this duration is represented as 3 pi by 2, and this duration is represented as 2 pi, and here this duration is represented as again continuously a periodic waveform is passing. Now let's consider, if you observe this circuit, this positively clamped circuit with respect to given input signal for the initial stage only, until the input is reached to minus Vm, diode is non-conducting here. But subsequent cycles, there is no need to identify the initial conditions here. But initial condition only, until Va is reached to minus Vm, the diode state is represented as your off state. So based on this point, here I represented as until it reaches to your minus Vm, the output voltage across the diode is represented as your 0. Hence, I represented as this is 0 up to this point, only the for initial pulses. For subsequent pulses, we can't identify this condition. Now we need to substitute what happens when Va is a 0, what is the output here? That is Vm. When Va is equal to Vm, so that output is represented as 2Vm. When Va is equal to minus Vm, the output is represented as 0. These are three parameters. We observe these mathematical relations. So by using this one, now I'm going to write. Now when Va is a 0, now at this point, what is the input voltage? That is a 0. When Va is a 0, what is the output voltage we observe? Vm here. So hence, previously the output is at the 0 voltage. Now this output is changing towards Vm. So hence 0 to Vm we need to take. So means in the positive direction. So let us take this point I consider as a Vm when Va is 0. Similarly, now I can observe the cycle. When Va equal to Vm, when Va is equal to Vm, what is the output voltage? Output is reached to 2Vm. Means already Vm is their previous value. Now it should be reached to another Vm voltage. Means now the signal is reached to your another Vm voltage, and this point another Vm. So total net voltage up to from 0 to this Vm, the total net voltage is 2V. Now similarly again, when Va is a 0, it reaches to your means 2Vm to Vm. Then again Va equal to minus Vm, output is a 0, means again it reaches to your 0. Now again when Va is a 0, V0 is reached to your Vm. So again when Va is a Vm, it reaches to 2Vm. Then again when Va is a 0, it reaches to Vm, like that. When Va is a minus Vm, it reaches to 0. So subsequently, but you can observe this one, only the initial clock pulse, initial stage, we identify that diode is non-conducting up to this point. Once the diode is conducting, then automatically generates the periodic signal waveform. So now this is a response of the positive clamping circuit. You can observe this input and output. There is no change in the response, but only the thing is that the DC level adjustment here. You can observe here in an input signal, the total magnitude is peak to peak voltage is 2Vm. Why? Because this is the Vm, and here this is also Vm minus Vm. The total peak to peak voltage is 2Vm. Here also in output response also, the total peak to peak voltage is here 2Vm. Now we need to check that. So this is the Vm line, this is the 2Vm line, this is the 0 line. Now we need to identify that what is the DC level here. If you observe the input signal, the average value or a DC value is 0. But coming to this output response, now we need to find out the average value or a DC value. So how we can identify this average value with respect to your input? Means, so in an input signal, the average value is a 0. Hence, we need to find out at Va is a 0, what is the output voltage? At Va is a 0, what is the output voltage? Output voltage is at Vm. So hence, so this is the DC level. So here it is called as DC level. So now from this point, here the DC level is adjusted in the positive portion. ends, it is called as a positive clamping. So why it is called the negative peak clamper means this entire the negative portion is raised at the above the zero level. So hence it is also called as your negative peak clamper. So up to this point, we discussed that what is the clamping and what is negative clamping and your positive clamping here. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.